Well, now I feel I have to live up to that. That's a bit scary. Okay, so thank you very much. My name is Dr Curran and I am a tissue engineer. Sounds like a little bit of an opening statement at an Alcoholics Anonymous meeting. Not that I'd know, but some people in the audience have told me. So if I do my job properly over the next 10 minutes, what I will do is give you an insight into what a dynamic, exciting and also evolving world that tissue engineering is. And so the title, Tissue Engineering, the gift that keeps on giving, or a bit of a turkey. You notice I worked hard on the Christmas theme there, but also tissue engineering is subject to a lot of media hype. The successes, the one-off successes are all over the media, but realistically, is it going to live up to its potential or fall flat on its face? So within the brief, we were told you've got 10 minutes to talk about yourself. Those of you in the audience who know me know that I would love that. Bit of background about how I ended up doing what I'm doing. So firstly, influences at school. For me, it was chemistry, biology, maths. So I was told, oh, you've got to be a medic, should be a medic. I never thought anything about that. I just did it. I just applied to be a medic. You can see that never actually quite panned out, because also at school I got a bit interested in boys going out and underage drinking. So, luckily though, I had this nickel and doubt in the back of my mind. And then when I got my grades and I got that phone call, oh, congratulations, I'd like to offer you a place, that niggling doubt actually came out as, I don't want to do it. Very luckily as well, my parents were away, so I didn't have to tell them about this momentous choice I've made. But then I also got another call saying, actually, we've got a new degree course starting, clinical engineering with material science. Once again, based here at the University of Liverpool. I was like, yeah, okay, cool, I'll do that, I'll give it a go, because I still didn't fully know what I wanted to do. So I started my degree and it was great. That was the beginning of it for me, because it was multidisciplinary. We did material science, we did engineering, physiology, anatomy, cell biology. You know, there I learned all the different principles of what made a material, what we need to consider for making a material, how we need to put materials into the body to replicate tissues and the loads and the stresses and strains. And it was great, because I got, again, to keep this variety, my basic understanding in chemistry, biology, maths, but also be able to apply it to various sort of specific clinical situations. And so that led me on to my PhD, which was in bone biomaterial interactions. And that sort of, again, kept the multidisciplinary nature, but it elevated a bit for me, because it was commercially funded by a multinational company. So again, I got to do the science, but I also got a window into the commercial expectations of these medical devices, what companies expect, and also what patients and clinicians expect. So as I'm sitting in my little lab doing what I needed to do, I also got a feel for what the impact of this could be. It would make a difference. And for me, that's the exciting thing about tissue engineering and what I do. So my PhD, Bone Biomaterial Interactions, is a classic example of why we need tissue engineering. It was designed to produce materials that could work with hip implants when you all go, not when you all go, sorry, I'm not wishing that on you, but if you ever need a hip implant. A lot of the time, if you do need a hip replacement, you've been in an accident or you've got some sort of disease, chronic disease that's, you know, affected your bones. And so realistically, you can design the best hip implant with all the right materials and all the correct weights and densities, but you've got to think about what you're putting it into. You put it into this femur that could be diseased or damaged, and you've got to sort of get the integration between this hip implant and the bone as tight as you can right at the very beginning. Otherwise, you won't get bone falling up to the implant and it will just fail and you're in a worse situation. So what people do, and still do, is we use what are called autologous bone chips. And what that entails is you're there on the operating table, as well as having your sort of hip ripped apart, they will go into your pelvis, take a bit of bone from your pelvis, grind it up, put it into the femur, and then put the hip implant on top of that. And this autologous bone chip layer acts as a sort of intermediate layer between the bone and the hip implant, encourages new bone to grow up to the implant, and also allows the correct transfer of stresses and things. So again, you know, that is what is accepted. That was called the gold standard. So you can see there's a massive need there for us to develop materials that we can use, that we don't need to operations. We don't need to harvest bone from you. We can simply replace those bone chips with a synthetic material. And so again, you know, the reason why I like doing what I'm doing and I can do what I do is I like variety. I like being able to break things down, scenarios, problems, see how they work, then learn from that, adapt and try and make things better. And that was probably the engineer in me, and that's why I've come back to an engineering department as well. So that was essentially biomaterials. That wasn't really tissue engineering. The field's moved on from biomaterials and evolved into this tissue engineering. So what is tissue engineering? Traditional tissue engineering is essentially largely reliant on cells that we take from you. For the purpose of this talk and the rest of my research, I'm going to concentrate on stem cells. So what we do is we take a biopsy from you, we grow these cells, we isolate them, because a lot of the time that we take these cells, they aren't exactly what we want them to be. So if we take bone marrow, you've got a lot of different cells in there, so we need to isolate them out, get the right type of cell, grow them. It needs what we call tissue culture flasks. Within these flasks, all the cells are receiving different stimuluses from this underlying material, and start to get different populations of cells. But traditionally, we ignored that and we carried on. We said, oh, we're getting some kinds of cells grown. We'll carry on, we'll expand them up to great expense, lots of different media, cytokines, growth factors, biological agents. Then when we've got the right number of cells, we put them on this scaffold. This scaffold, again, a lot of research-intensive activity to produce a scaffold. There's the right size, shape, got the right mechanical, dynamic properties, porosities. There's so many different things that can affect this scaffold and what its use will be. Then when we've got cells on this scaffold, we tend to put it back into the lab environment and stimulate it again with different things. It could be mechanical, sort of cyclic loads or tensile strengths to get cells aligned or the cells to start to form tissue. And also growth factors, cytokines, again, these biological agents. So what you can see from this simple schematic, and it is oversimplified, is that it's a multifaceted process. Lots of area for things to go wrong, lots of area for additional cost. So maybe it's time for change, and this is what we work on. Maybe it's time to start looking at these materials. Can we develop these materials and the properties of these materials so that we can just implant them directly into you, and the material itself will stimulate your cells, and we can get rid of all of these biological and mechanical factors. We turn your body into a bioreactor, essentially. So stem cells. Everyone will have heard about stem cells. They're your super cell. They will go to the site of injury or infection and turn on to be whatever cell type they need to be and make whatever tissue you are missing. So from an engineering point of view, what we ask is, can we engineer materials where we'll induce differentiation, that is, turn on a stem cell to be another certain type of cell, be it bone, cartilage, fat, nerve, muscle, whatever, that can effectively mimic the naturally occurring niche. What I mean by that is, if you think about your bone, your cartilage, straight off you know these two materials have very, very different properties. Bone, very hard, very rigid. Cartilage is your body's natural shock absorber, so it has to be more compliant, more open, more spongy than bone. Stem cells can turn on to be those two different types of things. So how can we do that? How can we make materials to do that? We have to get down to the nanoscale. This is where it gets interesting. They bind here with integrins, 8 nanometers. These integrins form focal adhesions, 80 nanometers. So cells can sense and respond to stimuli at the nanoscale, and what we need to do is be able to make cost-effective materials that provide these stimulus at the nanoscale. We can do this by lots of different ways. We've made model surfaces to produce chemical nanoarrays that control stem cell responses. We can do this. We can make surfaces that make super stem cells. We don't need to hit them with biological factors. Just put them on this surface, the stem cells kick in, the material defines that stem cell, the way it adheres, becomes this really superior type of stem cell. We can then do things like we can control alignment. If we can control alignment of these cells, we turn them on to make a totally different type of tissue. Cartilage, tendon, ligament, or now what we're moving on to is nerve. So why? Why do we do this? We're an aging population. Not only are we aging, we also demand a better quality of life. When we retire, we don't just all want to sit there, watch Jeremy Kyle this morning, whatever. We want to get out there and do stuff. For that, we need mobility. So there is a demand for this. Not only is there a demand, the way we need to work is that we need to make these things, we need to make them better, we need to make them more, and we need to make them more cost effective. So this is the guy we're sort of working to. 102 years of age, running marathons. This is the sort of challenges that we're facing. And I will stop there with my 10 minutes done.